Good afternoon. Uh, this is Professor Venkatashanti. Um, Today is September 4th. I'm here for the live session held on ME75, a short lecture series on complex variables with a focus on contour integration. Let's see, maybe I will start with the questions that were already posed, and I had given the answer on the platform. I will repeat that just in case you didn't understand what I meant in writing. So I'll take up the first question here by Mr. Sivaramakrishna. I want to write here. So his question was, if a function is not analytic at a point z0, then how it can be analytic in the neighborhood? Because it is not analytic at z0 means it has no derivative at all points in the set. Okay, so now let's say we have a function. Just for the sake of it, let me take f of z is equal to, let's say, 1 over z minus 1. Okay, so this looks like this. So there is this point 1, and let's say there is a neighborhood. Okay. Now as I approach limit z tending to 1, f of z is equal to limit z tending to 1 over z minus 1. It is obvious that this limit will blow up, it will go to infinity. Okay, but if we don't approach 1, if we leave out this point 1 and remain anywhere away from it, then there is no problem. Okay, the function is well defined and finite and continuous. Okay, so I can take a derivative, so I'll get minus, okay, f dash of z. If I take it will be minus 1 by z minus 1 whole squared, and this exists whenever I don't approach z equal to 1. There is no problem with the function if I don't approach z equal to 1. So the function is analytic everywhere. Okay. So let me read the response. Consider a real function for the moment. Forget complex variables. If this real function is a step function, so what I mean by a step function is, this is my axis and the function is a step function. It goes let's say 0 for a while, then beyond a certain point it goes constant. It's a step, it takes a step over here. Okay, now this function has a derivative here, there's no problem. It may be 0, but it has a derivative everywhere here. It also has a derivative meaning a defined slope. Okay, so it has a defined slope, it is 0. Similarly, it has a defined slope over here, but at this point there is a discontinuity in the function and hence the slope, so it is not analytic over here. If I take a derivative from the right side, I get one value. If I take a derivative from the left, I get another value. So this function here is not analytic over here, but that is just at one single point. Okay, so there's just one single point, so there is no problem. If a function is not analytic at just one point, it can be analytic everywhere else. There's no problem. Okay. If this real function is a step function that has a jump at x equal to x0, then to the left and the right of this point the function is well behaved and will have continuity and differentiability. You can draw a simple step function and see for yourself. Similarly, in complex variables, singular points are isolated points where the function is not differentiable. Okay, just like this. So this is an isolated point. Z minus 1 is an isolated point. Everywhere else the function behaves well. Take a derivative of 1 over z minus z0. In this case z0 is equal to 1. And if z is not equal to 0, that means z is not equal to 1, then the answer is minus 1 over z minus z0 whole square, which is this. At z equal to z0, that is 1, there is no derivative. Okay, because of non-analyticity at a single point. So the function is not analytic at a single point. If we say that this function is nowhere analytic, okay, then you will either have totally analytic functions or totally non-analytic functions. So that's not the case. Okay, and in fact functions like this are interesting because we have Cauchy residue theorem, and we can integrate around them, find residues and so forth. Okay, so function can be non-analytic at a point, but around that it can be well behaved, no problem. Okay, so maybe I'll take up the next question that was posed by Nidhi Satish. What is the basic procedure to evaluate residues? Could you please elaborate a little on it? Okay, so let's look at that question. Maybe I'll keep this page for somebody who comes late. Okay, so let's say first we need to get the order of a pole. Okay, if I have a function f of z, then what is the order of the pole? What is the order of the pole? Okay, so suppose I have f of z generally given by, let's say, p of z by q of z. Okay, and let me say in this case I take the example, let p of z be equal to z plus 1 whole squared, and let's say q of z is equal to z minus 1. Okay, so that means my function looks like z plus 1 whole squared by z minus 1 z minus 1. Okay, and obviously at z equal to 1 the function blows up, tends to infinity. So z minus 1 is a pole. Okay, so what is the order of the pole? Okay, so the order of the pole is I take the limit z tending to 1 z minus 1 into f of z. Okay, into f of z. So what is this limit? Limit z tending to 1 z minus 1 z plus 1 whole squared by z minus 1 is equal to This z minus 1, this z minus 1 cancel, and I get 1 plus 1, 2, 2 to the power 2, that is 4, which is not equal to 0. Okay. And this tells me the order of the pole is 1. Order of the pole is 1. Okay. We'll do another example that will make it clear. Okay. Now suppose I have f of z is equal to again p of z by q of z, and I choose p of z to be equal to z plus 1 whole squared and q of z to be equal to z minus 1 whole squared. Okay, you can see that at z equal to 1 again the function blows up. There is a problem. Okay, so my function now looks like z plus 1 whole squared by z minus 1 whole squared. Now what is the order of the pole? First I do limit z tending to 1, z minus 1 f of z, or equal to limit z tending to 1, z minus 1 into z plus 1 whole squared by z minus 1 whole squared. In this case 1 z minus 1 cancels off, but one of them remains. This limit is infinity. So we still have a difficulty over there, still blowing up. So then I do limit z minus 1 tending to 1, sorry, z minus 1 whole squared f of z, which is equal to limit z tending to 1, z minus 1 whole squared, z plus 1 whole squared by z minus 1 whole squared. Now this cancels with this and I get 4, which is not equal to 0. So the first time I get the limit not equal to 0, that is the order of the pole. So my order of the pole is 2. Order of the pole is 2. Okay. Now suppose I have a function where now q of z is equal to z minus 1 to the power p. P is some integer. And then this function is z plus 1 whole square by z minus 1 whole to the power p. Now if I continue in this manner until I come to limit z tending to 1, z minus 1 to the power p, z plus 1 whole square by z minus 1 whole to the power p, I will continue getting infinity, and this is the first time I will get a finite value 4 here. Okay, but if I do the next one, if I do any more, limit z tending to 1, z minus 1 to the power p plus 1, z plus 1 whole square by z minus 1 to the power p, this is going to be equal to 0. Okay, so in general what we say is if limit z tending to 1, z minus 1 to the power k, f of z is not equal to 0. It should not be equal to infinity or either. Okay, because the polarity is it's still a pole, but this is a check. Limit z tending to 1, z minus 1 to the power k, f of z is not equal to 0, then the order of the pole is k. Order of the pole is k. Okay. Now for the residue, there are one or two methods to find residues. Okay. If you have a simple pole means order is equal to 1. Okay, so let's see, f of z is equal to again some p of z by q of z, that is equal to, this time for again I take the same example, z plus 1 whole squared by z minus 1. Okay, then the residue of f of z at the simple pole z equal to 1 is given by limit z tending to 1, z minus 1 into f of z, or in this case limit z tending to 1, z minus 1 p of z by q of z is equal to limit z tending to 1, z minus 1, z plus 1 whole squared by z minus 1, that is equal to 4. Okay, so that is your residue. Now if you have a simple pole, there is another way to find the residue. Okay, I will not derive it, but I'll just give it to you. So f of z is the same thing. Okay, in this case p of z by q of z, and that is equal to z plus 1 whole squared. Okay, let me write the residue first. Okay, so the residue now, the residue is equal to limit z tending to 1 p of z by q dash of z. Okay, so you can see p of z is z plus 1 whole squared, q dash of z is 1, limit z tending to 1, that gives you 4. Okay, so these two, this holds for simple pole. Okay, this also holds for simple pole. Okay, if you have multiple order poles, so now poles of higher order, okay, so suppose I have a function f of z, okay, again some p of z by q of z. Okay, and I'll take the same p of z, let it be z plus 1 whole squared It can be something else also, doesn't matter. And q of z is, let's say, z minus 1 whole cube. Okay. Obviously, z is equal to 1 is a third order pole. You can check that by the previous method. Okay. Now the residue is given by z minus 1 whole cube f of z. Okay, first you do z minus 1 whole cube into f of z, and then you differentiate this twice. That means this is 3 minus 1. Okay, 3 minus 1, and divide by 3 minus 1 factorial. That's the residue. Okay, so in this case, let us see what happens. In this case, z minus 1 whole cube f of z is equal to z plus 1 whole square. I'll open that out. Z square plus twice z plus 1. Okay. Then I need to take two derivatives. So one derivative gives me yz plus 2. A second derivative gives me 2z. 2. Second derivative gives me 2 divided by 3 minus 1 factorial, which is 2 factorial, which is 2, is equal to 1. Okay. So if you have, so first is to find the order of the pole. That's important. Only then you can find the correct residue. And once you know the order of the pole, you do this mechanism. Okay. So if you have pth order pole, this will become p. The number of derivatives will be p minus 1. This will be p minus 1 factorial. Okay. So that's the most. So it's one way simpler for simple poles. If you have multiplicity of poles, if this and this holds for any function. Okay. I hope this clarifies the residue. Okay. So there was a question for exponentials and trigonometric functions. The same thing holds. Okay. Maybe if I have, okay, let's say f of z is equal to, let's say, 1 over z sine z. Okay. Now you can check that this has a double pole of order 2, pole of order 2 at z equals 0. Okay. Why? Limit z tending to 0, z into 1 by z sine z, okay, is equal to what? This cancels off. Sine z at z equals 0 is 0. It's in the denominator, is infinity. So I have not solved my problem. So limit z tending to 0, z square 1 by z sine z is equal to what now? So 1z cancels with this. I have z over sine z. Okay. Limit z tending to 0, z over sine z, which is equal to 1 and not equal to 0. So the order of the pole is 2. Okay. So what is the residue now? The residue is z square 1 over z sine z, okay, d dz, d by dz. Okay, so this is going to be equal to, and of course 1 by 2 minus 1 factorial, 2 minus 1 factorial, because it's 1, I left it off. Okay, so this becomes d by dz of z over sine z, okay, whatever that may be. Okay, so that is the answer to your residue question. Okay, now there was a question by Pratik Pandey. I'll continue. There was a question by Pratik Pandey on Cauchy-Gorsa theorem. Okay, it was a good question. There is not really much I can say, but let me just give the answer that I gave. His question was, during the proof of Cauchy-Gorsa theorem, it was assumed that f of z should be continuous to make partial derivatives of u and v continuous to apply Green's theorem. My point is, when you have already assumed function to be analytic, so derivative exists everywhere, and if derivatives exist, ux, uy, vx, vy should be continuous, as the sufficient condition for the existence of derivative. Was not your assumption ux, uy, vx, vy being continuous redundant, sir? Please give the explanation. Okay, a good question. I had already said whatever had to be said, so I will repeat that. Okay, and then you'll get a chance to ask. I said the theorems presented are fundamental theorems that were derived or discovered at the developmental stage of complex variables. Okay. Mathematics is a rigorous subject that does not assume anything. Okay. Okay. That means if f of z has a derivative, that the derivative is going to be continuous, we cannot assume. We have to come up with a proof. Okay. Till that is done, you cannot assume that the derivative also is continuous. Okay. Anything and everything has to be proved. If something is true for real variables, it need not be true for complex variables. Okay. Now, continuity is a necessary condition, not a sufficient condition. Okay. Look at a triangular function. I'll show you what I mean. Look at a triangular function. The function is continuous at the apex of the triangle, but the derivative does not exist. Okay. The left-hand derivative is different from the right-hand derivative. Hence, when you break up the integral f of z into real and imaginary parts, you get integral u dx minus v dy plus I integral v dx plus u dy. In order to use Green's theorem, partial derivatives of u and v must be continuous. In terms of f of z, this requires that the derivative of f of z be continuous. That is not yet proved. Not yet proved. F of z is analytical, then f dash z exists, but we do not know if it is continuous or not. This did not happen till Cauchy integral formula. Okay. Thus, to satisfy Green's theorem conditions, it was assumed that f dash z is continuous temporarily. Later, it was proved that once a complex function has a derivative, it has all orders of derivatives at that point. Then the continuity requirement was removed. A real function has a derivative at a point. It is not true that it has all order derivatives. Again, try a parabolic function. The derivative of a parabola is a triangle. The triangle has no derivative. I hope this clarifies. Okay. So please note, continuity of a function is a necessary condition, not sufficient. Okay. So what I mean by the triangle is that if I have this my axis and there is a triangle here, okay, so this is a continuous function, it's continuous everywhere. Now if I take the derivative of this function, then here the slope is positive, here the slope is negative, so you have, okay, so it will end up looking like this. Okay, so for a real function, okay, once a derivative, I mean, if you have a function and you keep on taking derivatives, it is not true that forever it has derivatives. So right here itself the derivative does not exist, because the left hand derivative and right hand derivative are not equal. And what to speak of this function here, the function is non-analytic further after the derivative. So for complex functions, once a function is analytic at a point, all orders of derivatives exist, which is not true for the real case. Okay, hope that is clear. There was a question by Harkirat. Sir, please again explain contour integration. Okay, so let me do that. Contour integration. Contour integration. So I'll take the simplest example we had. It was the integral minus infinity to infinity dx over 1 plus x square. Okay, I have always been calling the real integral as I. Okay, now we want to use contour integration on this. Okay, this can be done using real variable calculus that is there in the lecture and notes. Okay, so now I replace this with j, an integral over a closed contour. This represents my closed contour. I'm hoping it will be counterclockwise. Okay, C. Okay, and usually the x changes to z, so in this case this will be dz over 1 plus z square. Okay, now I am using complex variables in order to compute this value, this integral. Okay, and I have replaced the real line integral with a contour integral. So first of all, this part must be there as part of my contour. So this can, let me write it as dz plus, but on the real axis z is equal to x. Okay, so I must choose now a contour such that this is a part of that contour. Otherwise, choice of contour is pointless. So whatever contour I choose now, I will choose such that the real integral is one part of the contour integral. So I'm going on the real axis from minus infinity to infinity, and on this real axis z equal to x. Now what else can I do? I need to have a closed contour. I want a closed contour. Why do I want a closed contour? Because with closed contours I have Cauchy residue theorem to help me. That is the theorem, that is my bread and butter theorem to calculate integrations on closed contours. Okay, so if I go around closed contours and there are isolated poles, then I can find the value of this integral using residues at these isolated poles. That's why I need a closed contour. Okay, so now what are the poles of this function? Because z square plus 1 is in the denominator, this has poles at z is equal to plus I and minus I. So I have a pole here at plus I have a pole here at minus I. Okay, so now what do I do? This portion must be there. Okay, that is one requirement. Let's see. So this portion must be there. That's one requirement. It must be a closed contour. That is the second requirement. Okay, and then I can use residue theorem. So I come here. This must be there as part of my contour, and I go around an infinite half circle, come and join and make it a closed contour. Okay, so now I have a closed contour. Okay, so what is the use now? I have the portion I want, which is I. Okay, here z is equal to x, so this is I, this is the I. Okay, plus I have a portion on this circular half circle arc CR, so plus I have an integral on CR. Okay, that is equal to, now because it's a closed contour with an isolated pole inside, that is equal to twice pi I times the residue of what? Of the function 1 over z square plus 1, okay, at the pole inside. Pole inside is z equal to I. So I have all the portions here. I have the portion I want. I have incurred an extra portion because of closing the contour. That is equal to what residue theorem tells me. I get a lot of help from this theorem. Okay. Now idea, or the beautiful idea of contour integration is I will not touch this integral at all. In this case, it's very simple integral. Okay. It's a very simple integral in this case. But you could have something very complicated. I don't know what, sine of z cos hyperbolic z, z minus 10 whole squared by what, sine hyperbolic z. You name it, you can have anything you want. Okay, suppose this is what happens over here. Imagine trying to integrate this directly. So this sits over here, okay, as an integral which I will not touch at all. Okay, and then I choose a proper contour. Because I choose a contour, now I will get extra portions like this. Okay, then that is equated to residues if there are any singularities inside this contour. Okay, now what happens is, from the residue theorem I can change the, okay, I can get the value of this. Residue theorem gives me the value of the residue. Okay, and I have to calculate this extra portion which has come. Okay, usually by experience either that goes to 0, that means you choose a contour such that it goes to 0. In this case it does go to 0. Okay, I have in the denominator 1 plus the square plus 1, and z is going off to infinity. Okay, on this z goes to infinity. As z goes to infinity, this integrand goes to 0, so this integral goes to 0. Or usually it is integrable to some finite value. So in that case, what is my answer? Answer I is this residue contribution, minus the contribution from all the other portions. In this case, we just got one extra portion. You can get many more. Okay, you have seen keyhole contours where we had 0 to infinity, then we went around, we came down from the bottom, we came back. So I have portion 1, I have portion 2, I have portion 3, I have portion 4. Okay, so if there are poles inside, I get a residue contribution. Then I evaluate each and every portion, figure out whether this goes to 0, figure out whether this goes to 0 or a finite value, and that is the basic idea. The integral you want, you will not touch at all. That's the basic idea. Hope that's clear. Now it's time for you to ask me any queries. I'm here. Your PDF version is coming very soon. Okay, give me a day or two, the PDF version of the entire set will come. So that will be made available. Can I hear your names? How many are there? I know Patil is there. How to find, okay, there's like how to find residue at a point where f of z does not have an isolated thing. See, that's the whole point. Okay, the Cauchy residue theorem is with respect to isolated singularities. If you read the statement of the theorem, okay, the function f of z is analytic everywhere except at isolated points. Okay, the Cauchy residue theorem gives you an answer for such situations. Okay, if you don't have an isolated singularity, okay, all I can think of now is that you have a branch cut. Okay, that means one particular line is forbidden. When you have an isolated singularity, that point, isolated point, is forbidden. Okay, so if you say it is not an isolated singularity, for now at this level I will say that it is a branch cut. Okay, the branch cut is a singularity. Okay, because if you move around, the function changes, jumps values. Okay, however, it is not an isolated singularity. Then you have to do what we did. We deformed the contour, or around it we still try to find a closed contour. So we did problems using two methods. Okay, is that okay? So there the question of residue doesn't come. You have to find another means. There's no help for you to you have to find another means to do it.
Total 8 people watching here.
Maybe you can give me your names. I can see there are 8 people watching. So that distinction has to be made. We read a theorem statement and the subtlety we miss out. So the Cauchy residue theorem subtlety is isolated singularities. Okay. So if there is a branch cut, one entire line is not allowed. You can't cross. Then Cauchy residue theorem will not help you. in general, how did you find the series? The lecture series, how did you find? Or
There's a 10-second lag. So
okay,
we have to wait.
okay. I'm told there is a 10-second lag, so between my question and your response. So let me say before your responses come that when you deal with branch cuts and you try to find residues, okay, then the branch definition at the singular points must be respected. Okay, there are examples in the series where the isolated singularities are at plus I and minus I. Okay, now you don't straight away go and put I or minus I in place of the square root. Okay, you have given a definition for the square root with its angles. Using those angles, you have to define the location of the singularity. If you don't do that, you will make a mistake. Okay, so that's very important. So that has arisen in many of the cases, including where you had a pole on the branch cut. So the definition on the top of the cut and below the cut varies, so you have to respect that. Otherwise, you'll make a mistake in calculation. That's very important.
If we can wind up.
Okay.
If they don't have any questions.
It seems like you don't have questions. Shall I wind up? It is also possible that maybe you are not ready for questions today. I will ask the NPTEL authorities if just before the exam I can come and meet you so that you have more doubts and you are more ready for doubts and answers. I will see that. I think September 29th or so is the final exam. So before that I will see if what is the policy with NPTEL people. I don't have full authority. So I will ask them, and if they allow, we'll meet once again. Maybe you will be more ready with doubts. Okay. So we are closing now. Okay. There are no queries. We'll close now.